All right, so now we're going to talk about tangent vectors to quotient manifolds. Okay, and so we saw before that if you have tangent vectors of a submanifold which is embedded into a vector space, you can view them as essentially the usual classical notion of a tangent to the embedding of the curve. Okay, and sort of think of them, if you will, as arrows. It's like in the Euclidean space, which is tangent to the submanifold. Okay, so so before we saw that tangent vectors to embedded submanifolds can be viewed as sort of arrows in the sort of vector space which you embed in, which are just tangent in the usual sense to the submanifold. Technically, I guess it's like what we have is that it's tangent to the inclusion, it's like of that submanifold into the embedding space. But anyway, so so what we're interested in now is this idea of quotient manifolds, where you take an abstract manifold and you quotient it by some sort of equivalence relationship, and you want to ask whether you can do something similar. Okay, so for a quotient manifold, right? Let's think of quotienting the embedding space. So let's think of sort of the vector space E. It's like modulo some equivalence relationship. The situation is more abstract. But let's see what we can do. Okay, so let's just say this with a little bit more generality. So for generality, right, you consider an abstract manifold. M bar, and a quotient manifold M, which is just this M bar quotiented by the equivalence relationship, and there is a canonical projection. Okay, and if you recall, it's like what the canonical projection does is to take an element of M bar and associate it with the equivalence class, it's like which contains that element. Okay. Okay, so so you let C be an element of the tangent space at X. It's like to this quotient manifold M, right? And you let X bar, right, be an element of the equivalence class. Pi inverse of X. Okay, so if you have this, so what's going on here is that X you should think of as being an element of this quotient manifold, right? And then if you take the preimage of that by the canonical projection, you get a set of points in M bar which are in essentially this equivalence class. Okay, so that's what's happening. And then X bar is just a element or representative element of that equivalence class. Okay. All right. So then any element C bar, right, of T x bar m bar that satisfies the property that the linearization of the projection of x bar cos C bar is equal to cos C, right, is a representation of cos C. Okay, so let's try to unpack that statement here, right? And I always find it helpful to, you know, do a diagram. It's I can show how the maps are related to each other, right? So what we have is we have M bar, which is sort of the big abstract manifold. We have a canonical projection to M, right, pi. Okay, and then we have the tangent space M bar, right? And it's like an X bar here. It's like, and then there's TXM, right? So this two things are related by essentially the tangent map to pi, which I should think of as being just the projection map, comma, d of the projection map. Okay, so what I mean by that is that I'm mapping the tangent space to. I mean, it's like it depends on what your notation. So if d is just the part which acts on, well, I guess it really doesn't matter. Yeah, so this really is just a map d pi, right? So it maps x bar to x. It's like that's what you want, right? X bar is just an element of this pre-image. It's like of x by the projection. So x bar by definition will project down to x, and then m bar projects to m, and then it's like its action on tangent vectors is by the linearization of the derivative of the projection map. Okay. Okay, so you're saying that you have a C bar and you have a C here, right? So you just want to find something that's like a C bar, which is going to project to C in essence, right? And if you, yeah, so if you prefer, you can think of this as being just an element of the pre-image of d pi. It's like applied to cos C, right? So that's sort of an equivalent way of thinking about this, all right? So the same way that you find a representative element of an equivalence, sort of a quotient manifold, it's like by looking at the pre-image of the projection map, you do the same thing. It's like you look at the extensions, like to the tangent spaces, and you do the same thing, right? So again, this is not so surprising. Okay, so let's try to be a little bit more concrete with this. So let me just maybe keep this picture in mind. Okay, so for f is a map from, say, the manifold to the rails, right? We have a function f bar, which is a map from, which is just f composed with the projection map, right? Which is a map from m bar to the rails. Okay, so this is sort of a sort of invariant extension, if you will. It's like of f. It's like to the full space, right? So you can easily convince yourself that all you're really doing is to say that it's like f bar is going to have the same value on every element, which is in the same equivalence class. Okay, and yeah, so that's basically sort of some invariant lifting. It's like of the f here. Okay, so then in that situation, one can talk about the linearization of the derivative of f bar, evaluate x bar because c bar, right? So this is in the sort of the unreduced space, if you will, right? And then this is equal to df pi x bar, right, applied to d pi x bar because c bar. And that's okay, just equal to df of x because c. Okay. So the only problem, if you will, is that you know there's no uniqueness that's like in the choice of representatives, right? So a difficulty is that there are infinitely many sort of equally valid representations c bar of c at x bar. Okay. So so you want to, ideally it's like to define some sort of unique notion, right? So it's desirable to have a unique representative lifted representation of tangent vectors. Okay, so maybe sort of let me try to give you a picture of this, right? So if you have a big space, let's think of this as m bar, and then you have this little space down here, m, and there's this projection map pi, and you have a vector, right? There are many ways to lift this vector, if you will, right? There are many things which will all project down to the same vector, if you will. And intuitively, if you look at this picture, you can think of it as having a horizontal space and a vertical space, right? So there's some way to think about identifying. Okay, so let's see what happens here. When you have the projection, that gives you a natural vertical direction in this picture, right? So what you want to do then is you want to identify something which is complementary to this set of, it's like fibers, if you will, which are the pre-image of a point, okay? So how shall I say this? So if you have a point x here, you have, okay, so say you have a point x here, right? There's this pre-image, which is pi inverse of x, okay? And so this is something which is an m bar. You can talk about the tangent to that, and you should think of the tangent to that as defining a vertical space, okay? So, and you can convince yourself, I mean, it's like it's so easy to see intuitively that this m here, which is the quotient space, right, needs to be identified with something which is complementary to this well-defined vertical direction which comes from the canonical projection. So I want to define some sort of horizontal space, if you will, right, which then is identified with this piece here, which is the manifold, okay? And I mean, I'm just doing this at the level of tangent spaces, okay? So I'm not caring about what happens away from it, okay? So so how should I do this, right? So the intuition is that the canonical projection, right, pi, right, gives a fiber pi inverse x over each point x on the quotient manifold, right? This induces the notion of a vertical sort of subspace. So let's call that well, let's not call it anything. Well, let's call it Vx bar, right? Which is really like the tangent space at x bar of pi inverse x, right? Something like this. Okay. Then you want to find something which is complementary to that, and that's once you've chosen that complementary horizontal subspace. And what I mean by complementary is that then the span of vectors in this Vx with the span of the vectors in that horizontal subspace is the whole tangent space. At x bar, it's like 2m bar. Okay. All right. So let me try to be a little bit more precise about this. And okay, but you know, before we do that, let me sort of say how, if you had this choice of a horizontal space, then you have this uniqueness, if you will, right? So the point is that then you want to lift this vector to something in that horizontal space, right, which projects then back down. It's like by the projection map, by the linearization of projection map, or derivative projection map to the original vector you had. Okay, and so this is what is called a horizontal lift, if you will. Okay, and then that's where you're going to get this uniqueness of the representation. Okay, so right, yeah. So that's what I said here, right? Vx bar is equal to the tangent space at x bar of the fiber over x. Right. So this is the vertical space at x bar. Okay, so I want to assign a horizontal space at each x bar that is complementary to this Vx bar. Okay, so what do I do here? So I have a mapping let's call that H. Okay, that assigns to each x bar of m bar, a subspace. Let's call that H sub x bar, which is contained in Tx bar m bar that is complementary to Vx bar. Okay, what that means is that Hx bar direct sum Vx bar, right, is the entire tangent space Tx bar m bar. Okay, and then the intersection is just the zero vector, right? Okay. All right, and this choice of mapping is called a horizontal distribution. So this is called a horizontal distribution. On M bar. Okay. And then, so the mapping H is called horizontal distribution, just to be clear, right? Then Hx bar is the horizontal space. We have vertical space is the, and Hx bar is the horizontal space. At x bar, right? Okay. So the point is that once you have this idea of horizontal distribution, and in particular, for every point x bar, it's like in M bar, you have this split of the tangent space into horizontal and vertical subspaces, right? Then there's a unique horizontal lift. Okay, so once we have this, once we have a horizontal distribution, right, there's a unique element C bar x bar, which is contained in the horizontal space with the property that it projects to the C. Okay, and this is called, this unique element is called the horizontal lift. Okay. Yep. So, all right. So anyway, so the point, if you will, is that this just gives you a way of picking a canonical representative. It's like of this equivalence class of tangent vectors, which you know, once you specified again this choice of a complementary subspace. Okay. And that's basically how oftentimes you work. It's like with tangent vectors to quotient manifolds, is that you endow this quotient manifold with this horizontal distribution, which is complementary to the canonical projection, or to, shall we say, the vertical space, which is induced by the canonical projection. Okay, so let me just stop here for now.